solutions with concentration for conservation laws is discontinuous fluxes and its application to the numerical schemes for hyperbolic systems. So it is a joint work with Iman Sahu, Ekta Agarwal and Ganesh Vaidya. So So the outline of the talk is that conservation laws will discontinuous flux and existing notion of solutions, questions and difficulties, and vanishing viscosity approximation and its limit, and finally some numerical skills. Okay, so first we'll review what is conservation laws with discontinuous flux. It is so a well-studied form of conservation laws with discontinuous flux function is ut plus fux equal to 0, where x and t are in r cross r plus, and u of so initial data is in bounded measurable function u naught, and the capital F can be written as Heaviside function into fu plus 1 minus Heaviside function into gu. Where in general f and g can be Lipschitz functions, but here we are taking f1, f and g are c1 and strictly convex on R. So what are the existing notions? Adimukti et al. Gave an Laxonic representation for if when f and g are in C1 and strictly convex with superlinear growth. Superlinear growth, by superlinear growth mean that limit mod u tends to infinity, fu by mod u is going to be plus in infinity. So next thing that Adimukti et al. Studied the concept of AB entropy solutions with following assumptions on the flux function. So f and g can be both can be convex or both can be concave, and f can be convex or g can be concave or vice versa. But there's there's one condition that they should have a unique minimum or unique maximum. Okay. So now one can ask the following questions. What happens when fluxes are not strictly convex? For instance, fluxes with f dash 0 is less than 0 and g dash is greater than 0. And what are the existence and uniqueness for an overcompressive flux pair? So by overcompressive flux pair, we mean that f and g are strictly convex, C1 strictly convex, and f dash prime is less than 0 and g dash prime is bigger than 0, and f and g are non-linear objects. Okay, so so one can easily observe that if we have the condition 2, then the flux function already loses the superlinearity condition, but still we can give a lax Olenek representation that we will see in the next slides. Okay, so the difficulties, what are the difficulties? The first difficulty is that since the characteristics meets at the interface, it may happen that there does not exist a bounded width solution. So therefore, a notion of measured value solution has to be introduced. AB connection does not exist for when the fluxes are f dash 0 is less than 0 and g dash 0 is greater than 0. In 2, Adimukti et al. Gave a notion of bounded solution by relaxing the RH condition. So, but that does not conserve masses. So in conservation law, we always seek solutions which conserve mass. So how we overcome these difficulties? So we propose a delta shock at the interface. This solution conserves mass and more physically significant. We use vanishing viscosity method for linear fluxes, and a Laxonic type formula is given for non-linear fluxes with overcompressive flux pair. And finally, some convergent numerical schemes are proposed to capture delta shock. So what is the definition of measured valued solution? A measured valued solution U equal to U bar plus WT into delta is said to be a generalized weak solution if the following integral identity holds. So where WT and U bar of xt are locally bounded functions. So WT we call weight of the delta shock. Vanishing viscosity approximation. Okay, so we use vanishing viscosity approximation when the fluxes are of linear type. So we use what is vanishing viscosity approximation? It is just, and you add a epsilon uxx term in the right hand side for when epsilon is strictly positive, and then you pass to the limit as epsilon tends to 0. So the idea is to restrict the above equation 2 in the in two quarter planes, putting a boundary condition u of 0 t equal to beta t, and to show the existence of C1 solution u epsilon when epsilon is strictly positive in the half plane for the viscous equation. In this case, we can explicitly find a formula of beta t and show that the boundary function is independent of epsilon. Weak formulation for the viscous equation. Okay, so a function u is C1 means we want u is C1 in the space variable only. Here is called a weak formulation for the above problem if it satisfies the following integral identity. Okay, so for that integral identity has to be hold for all P which is compact, suppose for all smooth P with compact. Okay. So the vanishing viscosity approximation, we gave the first theorem here that explicit solution to the equation 2 in the above sense is where u1 is the 5, equation number 5, u1 is the solution in the right half plane and u2 is the solution in the left half plane. Okay. And where E alpha alpha is being a meta-Glassler function with alpha and alpha tilde is positive. Okay, and here as we said earlier that we can explicitly compute what is the boundary function beta t, and here is the explicit form of beta t in equation 7. And so what is the sketch? So how to characterize the function beta t? We have assumed that the solution is C1 in the space variable as we can see in the definition. So u1 x epsilon 0 plus p should equal to u1 u2 x 0 minus p, and if we equate that we get an and we use integration by parts formula, we get a non-homogeneous fractional differential equation. Now we have a ready formula for equation 10, which gives the boundary function, and where and that boundary function involves that meta-Glassler function, which is of the form z power k by gamma alpha k power alpha till the summation of that series, and this gamma is the usual gamma function. From here we get an explicit form of beta t. Okay. So now the next thing is the vanishing viscosity limit. Vanishing viscosity limit means what we got, what the solution we got for epsilon positive. Now we need to pass to the limit as epsilon tends to 0 in that solution. For that, it is important to get a bound of on beta t, which is independent of epsilon, and here we can get a more more nicer bound, which is independent of t also. So the sketch of the proof is very simple, that we use a recursive relation for the meta-Glassler function and in some change of variable formula. So now this is the final result where we can see that we have a delta wave, delta shock in that solution at x equal to 0. Okay. So where u naught is the u naught, capital U naught is defined here, and uxt is given by equation number 12. So the sketch of the proof, that first u1 we can write as a differentiation of some function, and u2 also we can write as a differentiation of some function. Then now we define capital U as P and Q, P in the right half plane, Q in the left half plane, and we pass to the limit in the sense of distribution, and we get limit of capital U epsilon t is capital uxt and is given by equation 15, and then the with derivative, the distribution derivative of capital U gives the small u, and we get the desired result. Now we come to the non-linear case when f and g are non-linear. So for that we aim to give a Laxonic formula. Okay, so the first lemma is that let v be a ellipsis continuous function in r minus 0 cross open 0 infinity, which is a viscosity solution of vt plus g of vx equal to 0 in the left half plane and vt plus f of vx equal to 0 in the right half plane. Then its distribution derivative satisfies the weak formulation. So now one thing here is to note that what I was saying in the beginning of the talk, that I mean, if we have the condition that f dash is less than 0 and g dash is bigger than 0, we lose the superlinearity condition, but still we can give a Laxonic representation because of the maximum principle, because when we assume that u naught, the initial data, is a bounded measurable function, and if u naught is in small f to capital F, then we can extend our the flux, the only, I mean, where the fluxes are only matters, it is a compact set M to M. And if we extend f by f bar and if g by g bar, which is, and g bar and f bar are strictly convex with superlinear growth, such that if f bar equal to f in the compact sets, then we can extend our, and then we can all give a Laxonic representation for non-superlinear functions, the flux function which is not superlinear. Okay. So this is the Laxonic formula where f bar and g bar, f bar star and g bar star is the convex dual of f bar and g bar, and u naught belongs to capital M to a small m to capital M, and v naught is 0 to x u naught of SDS. So we define the cost functional v1. V1 is the minimum we are taking in the left half plane, and v2 minimum of v2 is on the right half plane, and it is defined in the following way of 16 and 17. And as I said, the g tilde star is the convex dual of g tilde, g bar, and f tilde star is the convex dual of f bar. Okay, yeah. So then the Laxonic type formula is given by u equal to, if u equal to u bar plus wt delta naught is a solution of 1, and then the Laxonic type formula is given by Laxonic type formula for 1 is given by the following equation. U bar is of the form g dash prime g bar dash prime g bar dash inverse x minus y1 xt by t when it is in left, when x is in left half plane, and a bar dash inverse x minus y2 xt by t when it is in right half plane, and the weight is given by v20 minus v10 when t is positive. When and where y1 xt and y2 xt are the minimizers of v1 and v2 respectively at the point xt, defined as in 16 and 17. 16 and 17 means this by the cost function. Okay, now we come to the numerical schemes. Numericals, so we propose a, so we can see the final result. What is the final result for the numerical scheme? This is the final result, that if UH and WH be numerical approximations obtained from the scheme 19, so we define the scheme 19 as follows. A finite volume scheme is given by UIN plus 1 equal to UIN minus lambda of the Fi plus half minus Fi minus half n. So Fi plus half and I minus half are the numerical fluxes associated to the flux function. Okay, and it is given by 20. So the so if WH and UH and WH with a numerical approximation obtained from the scheme 19, assume that there exists a sequence HK which tends to 0 as k tends to infinity, such that if we set delta kt equal to lambda of hk, then WHK is bounded by k, and k is independent of independent of time, and 1 minus that characteristics function of minus hk by 2 to hk by 2 into uhk is bounded by k with the same k for some k constant, and then this 1 minus characteristic function of minus hk by 2 to hk by 2 into uhk is converges to u in the L1 loop, and whk is converges to the weight of the delta shock, and then we call that u plus w into delta shock is the weak solution of 1. Okay, so we also extended the scheme to the system. We can observe that if the first equation is a standard scalar conservation law, and second equation can be thought of as a equation with discontinuous flux function if a k dash is discontinuous. So we extended our schemes to for this systems also. And the one picture is going to show that it is a numerically verified that at x equal to 0, we have a delta shock at high, which weight is 3.0024. Okay. So these are the references. You can find details in the reference 4. Okay. And thank you for your attention.